Mathematical logic uses a simple notation to describe consequence. In the classroom, this is a clean pipeline. An axiom is assumed, a proof is a valid derivation, and a theorem is the resulting truth. But that definition fractures at the research level. At the frontier, an axiom functions as a rule-setting commitment within a formal language. A proof is a checkable transformation licensed by explicit rules of inference. The relationship between theorem, axiom, and proof has evolved from a mechanical record of facts into a dynamic, engineered architecture of consequence. To understand how modern AI can solve Olympiad-level mathematics, we have to trace the path that turned the theorem from an evident truth into a machine-checkable software dependency. The classical standard for mathematical truth was Greek demonstration. In Euclid's geometry, proofs were diagram-backed procedures. The axioms grounding these proofs were intended to be unquestionable starting points, direct descriptions of physical reality. This intuitive model held for centuries, until mathematicians attempted to prove Euclid's fifth postulate, the claim that parallel lines never intersect. In the 19th century, researchers built entirely coherent non-Euclidean geometries by warping this postulate. On a spherical surface, parallel lines eventually cross. This discovery revealed a deeper truth. If multiple incompatible geometries are valid, axioms are not universal descriptions of physical space. David Hilbert formalized a powerful new solution to this growing mathematical crisis. Hilbert reimagined axioms as structural constraints. They became implicit definitions, rules that dictate the permitted relationships between abstract placeholder variables. Modern mathematics was born in this shift, discarding physical intuition to study pure, permitted structural logic. This structural turn allowed mathematics to study its own methods. Proof itself became a finite formal object, a subject of mathematical investigation. Alfred Tarski distinguished two axes of validity. On the left, syntactic derivatability determines if a claim follows from axioms via mechanical rules, a valid movement through a system. On the right, semantic truth asks if a claim holds across every possible model of those axioms. The hope was that these two concepts would perfectly align, that every truth would eventually be captured by a proof. Kurt Gödel proved that this alignment is impossible for any system strong enough to handle arithmetic. His incompleteness theorems established that in any consistent formal system, there are true statements that the system's own rules can never prove. This result separated universal truth from formal provability. A system of logic is powerful, but it is not exhaustive. Theoremhood is relative to the rules of the system that generated it. A proven theorem represents a specific achievement within a chosen syntactic framework. As the limits of logic became clear, the focus shifted to the internal architecture of the proof itself. Gerhard Gensen developed natural deduction, providing an internal, analyzable geometry to the act of inference. Gensen treated proofs as transformable objects. Logical detours could be normalized into direct, sub-formula paths. This view of proof as an optimizable structure led directly to the Curry-Howard correspondence, the bridge between logic and computer science. In this correspondence, a mathematical proposition is functionally identical to a software data type. Likewise, a proof is functionally identical to an executable program. Constructive type theory dictates that to assert an object exists, you must provide the data to construct it. You are providing a program that computes the result. A theorem is a type. Proving that theorem means successfully inhabiting that type with an executable proof term. Classical proofs establish existence by showing that non-existence leads to a contradiction. Constructive proofs provide the actual algorithm. Through this lineage, the distinction between a mathematical theorem and a compiled software program entirely dissolved. This evolution defines the contemporary era. Mathematics is increasingly written in formal languages within proof assistants like Lean and Coq. These systems support recent structural revolutions, including homotopy type theory, which reconfigures the meaning of mathematical equality. The univalence axiom treats identity as a higher dimensional path. Equivalent structures can be identified as equal, internalizing the way mathematicians actually think about structure. Proof assistants verify these complex theorems by processing them through a tiny, trusted software prunal. Theoremhood is now defined as an artifact that successfully passes a deterministic check. It is an object of verified data. This is the environment where AI-assisted proving functions. Models like AlphaProof can handle Olympiad-level problems because they have a formal checker to verify their work. The roles are split. The AI conducts a probabilistic search for a candidate proof, while the formal kernel executes the absolute verification. A formalized theorem exists as a node in a massive dependency graph. Lean's MathLib is a growing ecosystem of these interconnected results. Each theorem tracks its own requirements. It explicitly logs every axiom it imports, from the axiom of choice to univalence, as modular dependencies. Formalization turns theoremhood into a discipline of software architecture, where every hidden assumption is transformed into explicit data. We can now return to the original triad of mathematical logic and view it through this architectural lens. An axiom is a source position, a specific design choice that builds a mathematical world. A proof is a path, a licensed, verifiable movement through that world. And a theorem is a target position, the stabilized consequence that remains once the movement is complete. These positions are dynamic. A theorem in one theory can become an axiom in another. Formalization and AI do not replace human intuition. They require it to interface perfectly with the absolute rigor of machine verification. Mathematical proof is no longer just the discovery of evident truth. It is the ultimate act of engineered consequence.